Alright guys, so I am at the District 15 district office today for a curriculum meeting, which is why I'm not at school today, so I have to apologize for that. But the good news for you guys is that I did make you a video, so you'll be able to learn the same material that we would have done in class today, and I could take any questions that you might have tomorrow. The bad news is all bad news for me. I tried making a video at 5 o'clock and the audio didn't work. It turned out that the audio drivers had to be updated on my computer. Then I tried another video at 5:40 and that one was all staticky because I got the wrong audio drivers. So now I'm on to the iPad and I'm going to try my iPad for this instead. So we'll see how that goes. So the third time is a charm, guys. Today what we're going to be talking about is a concept called improper integrals. And the idea with an improper integral is either the upper or lower limit of integration is going to be infinity. So we're going to infinity and beyond. Sometimes in both directions we'll be going to infinity. Just depends on the problem. So I chose Buzz Lightyear as our kind of cartoon sponsor for this. So he's going to be talking about to infinity and beyond. Well, actually just to infinity, not beyond. But, I mean, that's still pretty far, right? I mean, what does it even mean to use infinity as one of your limits of integration anyway? I mean, that's something we've got to talk about. And anyway, why is a cartoon talking about math? So maybe we should just move on. Cool thing about this iPad, by the way, look at this. I can do some pretty wild stuff with this app. So hope none of you guys get motion sickness, because you'd probably be getting, like, motion sick right about now. Okay, anyway, so let's move on. So let's do our first example. What we're going to end up doing is we are going to compute the integral from 1 to infinity of 1 over x squared dx. The integral from 1 to infinity of 1 over x squared dx. And in order to do so, first you probably should think about what's actually happening here. If we're trying to compute the definite integral from 1 to infinity of 1 over x squared dx. Really what's happening is we are finding the amount of area accumulated between the curve and the x-axis starting at x equals 1 and going all the way up. We're letting x tend towards infinity. So pretty wild stuff. We've got basically a geometric shape where the base of that shape is infinitely long, but surprisingly, we can accumulate a finite amount of area. So even though we have a solid, or a shape that is a region whose base is infinitely long, we're going to accumulate a finite amount of area between the curve and the x-axis. So that's kind of unexpected. So I don't know, why don't we work it out? So step number 1, and this is the most important first step. Before you do anything with antiderivatives, before you do any sort of stuff involving integrals, really the very first thing you need to do is rewrite your improper integral as a limit. Infinity as an upper limit of integration is not really valid. Infinity is not a number that we work with in this sort of math class. I mean, infinity is not an actual number, it's more of a concept for our purposes. So we rewrite this as the limit as b goes to infinity of the definite integral from 1 to b of 1 over x squared dx. After you complete that, then it would make sense to talk about the antiderivative of 1 over x squared. And you could see that right here. The antiderivative, once we rewrite this as a limit, we could say that the antiderivative of 1 over x squared is negative 1 over x. And that's going to be evaluated at x equals 1 and x equals b using the fundamental theorem of calculus. Moving right along, if we plug that b equals if we plug that x equals b in for x, and if we plug x equals 1 in for x, we get the limit as b goes to infinity of negative 1 over b minus negative 1. Now, as b tends to infinity, you guys know where negative 1 over b goes. That goes to 0. So for our limit, we're just left with the opposite of negative 1, which, of course, is positive 1. So there we have it. We have that the integral from 1 to infinity of 1 over x squared dx is equal to 1. Even though we have a region whose base is infinitely long, the amount of area between the curve and the x-axis is only 1 unit of area. So pretty shocking, actually. Now guys, since this is a video, feel free to have the teacher pause or rewind or anything like that if you do need extra time to write any of this down, because I'm not going to really pause that long between slides, especially moving forward. So let's go on to slide number 3. So for our next example, or for our next thing that I'd like to talk about, it's basically just a warning. It's something to look out for. A common mistake for students to make is to forget to use that limit notation. And I know it seems pedantic, I know it seems kind of picky and unfair to have to write limits all the time. It actually does matter, and it actually is important. So it is crucial that you guys don't accidentally take an antiderivative before you write a limit in the problem. So here's a version of the problem that you might see someone try. You've got to be super careful. This will get you 0 credit on the AP test. This will get you 0 credit on my test for this chapter as well. If you take an antiderivative and then write that the upper limit of integration should be x equals infinity and the lower limit of integration should be x equals 1, and then you try to evaluate the function at x equals infinity, to be honest, that's kind of nonsense. It doesn't make any sense to it for our purposes. So I'm going to warn you against doing that. So basically, if I see an antiderivative with an infinity written up top, or if I see you evaluating a function at x equals infinity, you'll get no credit for the entire problem. I don't foresee you guys doing that. You guys seem very vigilant and you pay attention to detail. So I'm not really concerned about it. But it's something to look out for, so don't do that. Okay, let's move on to another example, though. This one will have some partial fraction decomposition in it. Kind of cool stuff. So for example number 2, we are asked to compute the integral from 2 to infinity, of 2 over x squared plus 6x plus 8 dx. Now for this particular problem, probably the best road to go down before we worry about limits, before we worry about antiderivatives, before we do any of that new stuff, let's just do partial fractions. So our integrand was 2 divided by x plus 4 times x plus 2. If you factor that denominator, that's what you get. X squared plus 6x, x squared plus 6x plus 8 factors as x plus 4 times x plus 2. Now we want a partial fraction decomposition where we have an a over x plus 4 and a b over x plus 2. That'll eventually get us to a times the quantity x plus 2 plus b times the quantity x plus 4 is equal to 2. Now we can pick clever values for x. So a clever value for x would be x equals negative 2. That will give us b is equal to 1. And another clever value for x would be x equals negative 4, which will give us a equals negative 1. So you plug that in for a, you plug that in for b, and you've got your partial fraction decomposition. We're going to end up having negative 1 over x plus 4 plus 1 over x plus 2 is our decomposition. And that will get us back to where we left off. So we were supposed to compute the definite integral from 2 to infinity of 2 over x squared plus 6x plus 8. Our partial fraction decomposition will give us the definite integral from 2 to infinity of 1 over x plus 2 dx minus the definite integral from 2 to infinity of 1 over x plus 4 dx. Now at this point, before we can go any further, before we have any antiderivatives floating around, we need to make sure to convert to a form that has limits. So we have the limit as b goes to infinity of the definite integral from 2 to b of 1 over x plus 2 dx minus the definite integral from 2 to b of 1 over x plus 4 dx. Now we can do antiderivatives. Now it's okay to do that. So the antiderivative of 1 over x plus 2 is the natural log of x plus 2. The antiderivative of 1 over x plus 4 is the natural log of x plus 4. Now the fundamental theorem of calculus says we'll be evaluating that at x equals 2 and x equals b for both of those. Now if you're paying really, really close attention, you might see something that you interpret as a mistake. because you might have wanted me to put absolute value bars in those natural logs. You can if you want. That wouldn't be wrong to do so, but it turns out because of a subtlety, it's not strictly necessary in this case. The reason being, we are evaluating the natural log only at positive values because of the limits of integration that were given to us in the problem, so it ends up being irrelevant. But you can if you'd like to. Okay, moving right along here. Now let's take a look at after we plug the b in and the 2 in for x, after we plug the b in and the 2 in for x, after we use the fundamental theorem of calculus, we have the natural log of b plus 2 minus the natural log of 4 minus the natural log of b plus 4 plus the natural log of 6. Well, we could kind of take advantage of some of these properties of natural logs here. First of all, if we have the natural log of b plus 2 minus the natural log of b plus 4, we could condense that to the natural log of b plus 2 over b plus 4. Likewise, we could do the same thing with minus the natural log of 4 and plus the natural log of 6. Minus natural log of 4 plus natural log of 6 can be condensed to the natural log of 6 over 4. And then we can use either L'Hopital's rule or some of the tricks that you guys may have learned in a previous class, in your Trig Calc A class, for evaluating this limit. There's no calculus left, all it really is limits that are left. So we have the limit as b goes to infinity of the natural log of b plus 2 over b plus 4 plus the natural log of 6 over 4. I don't really mind how you look at this limit. If you like L'Hopital's rule, you can use that. So as b goes to infinity, we have the ratio of b plus 2 over b plus 4 here. And that's an indeterminate form. If you were to, let b tend to infinity, you'd have infinity over infinity. And since infinity over infinity is an indeterminate form, we can use L'Hopital's rule. The derivative of b plus 2 is 1. The derivative of b plus 4 is 1. So we end up with the natural log of 1 over 1, or just the natural log of 1. And the natural log of 1 is 0. So this entire beginning portion is 0. And then, of course, the natural log of 6/4 is the same thing as the natural log of 3/2. So there you have it all together. If you do want this paused, just feel free to ask your teacher to do so. But I'm going to move on, because we've got a lot to do. And I've been talking for about 2 hours straight, because I've done this lesson a bunch of times in a row. Okay, so at this case, is it the case that all improper integrals need to converge? That is, we've seen 2 examples now where we've had improper integrals that converge. Do they always converge? If I were in class today, we can have a discussion about that, right? Like, we can kind of talk about, would we expect that these improper integrals converge, or would we not expect that to be the case? And what we'd probably eventually get to is the conclusion that improper integrals probably don't need to converge. There probably are improper integrals out there that will go off to infinity, and to infinity and beyond. And the next example is going to be probably the simplest example of that occurring. So here we have it. Compute the definite integral, the improper integral, from 0 to infinity of 4 dx. So my lower limit of integration is 0, my upper limit of integration is infinity, and my integrand is f of x is equal to 4. The way that you guys should probably picture that, one way to imagine what's going on here, is we've got a rectangle where the rectangle starts at x equals 0, and then its base is actually infinitely long. So the base of this rectangle continues indefinitely to the right as x tends to infinity. And if you think about it, I mean, a rectangle with a finite height of 4, but an infinitely long base, that's going to be an infinite area. There's no way that that's going to be a finite quantity. So we've already kind of proven to ourselves that improper integrals probably don't need to converge in every single case. And this is a fairly quick example to work out. If we have the integral from 0 to infinity of 4 dx, first thing, before we do any antiderivatives, we need to rewrite that as the limit as b tends to infinity of the definite integral from 0 to b of 4 dx. Alright, now that that's rewritten as a limit, go ahead and take your antiderivative. The antiderivative of 4 is 4x. Fundamental theorem of calculus tells us that we'll be evaluating that 4x at x equals b minus evaluating it at x equals 0. And that will end up leaving behind the limit as b goes to infinity of 4b. And of course, if you let b go to infinity, then 4b is unbounded. It's going to tend to infinity. So, as you would expect, this improper integral diverges. It goes to infinity. So when I say, does this improper integral converge or diverge, I mean, is it finite or not finite, essentially. We'll talk about other things that can happen later, but for our purposes now, basically, does the improper integral work out to a finite quantity, or does it shoot off to infinity? Okay, the kind of strange thing, though, is it turns out this isn't the only way to make an improper integral diverge. I mean, this is a pretty obvious way for it to happen, right? You could think about what went wrong. And let's go to the next slide. So on this next slide, we could see basically that the thing that went wrong was this curve, this integrand, f of x is equal to 4, didn't really taper off at the end. That height didn't decrease over time. We didn't have a tapering as x went to infinity. But surprisingly, having the curve taper off at the end isn't even enough. So example 1 and 2, we had these curves where the integrand, if you graphed it, it tapered off as you went to the right. It got, the function itself went lower and lower and lower. It tended towards 0. And then example 3 kind of went haywire because this height stayed constant the whole time. Well, that's not the only way that we can diverge. We can also end up diverging for other reasons. So is it enough to take the limit of the integrand as it tends to infinity to determine if an improper integral converges? It turns out no. Here's what I mean by the limit of the integrand, by the way. You could see here the limit as x goes to infinity of 4 is equal to 4. The graph does not taper off. The f of x stays at x equals 4. In contrast, we had, a different integrand for a previous example. The limit as x goes to infinity of, we had 1 over x squared was one of the improper integrals we looked at. And the limit as x goes to infinity of 1 over x squared is 0. So that graph tapered off, right? Like that function on the right-hand branch kind of approached 0 as x went to infinity. I know it's shocking. Like this kind of blows my mind as well. Just because it tapers off at the end doesn't mean you're only going to accumulate a finite amount of area. Let's try the next example to see that in action. All right, so example number 4, compute the definite integral from 1 to infinity of 1 over x dx. If you just kind of observe the graph, you might at first think that this will end up being a finite amount of area, right? We're starting at x equals 1. And yes, the base of this region is going to be infinitely long, so we're going to let x go to infinity. But you might guess that the amount of area accumulated between the curve and the x-axis is going to end up being finite. And you'd be wrong, actually, surprisingly. So the nature of infinity is it's one of those weird things where your intuition from other areas of mathematics might not carry over that well when we're talking about infinity. So here we have the integral from 1 to infinity of 1 over x dx. Replace it first with a limit. The limit as b goes to infinity of the definite integral from 1 to b of 1 over x dx. I'm going to be very picky with this. I know I kind of warned you on a previous slide, but I am going to be very, very picky that every single time you write that as a limit. All right, so let's keep moving right along here. So now that we've rewritten as a limit, it's okay to take the antiderivative. And the antiderivative of 1 over x is the natural log of x. So we have the limit as b goes to infinity of the natural log of x, where x is going to be evaluated at x equals 1 and x equals b. So let's apply the fundamental theorem of calculus to get to this point. The limit as b goes to infinity of the natural log of b minus the natural log of 1. You guys are experts with your natural log properties, so you know the natural logarithm of 1 is 0. And you also know that if you let b tend to infinity, the natural log of b is also going to tend to infinity. Basically, the natural log function is an unbounded function. It's a monotonically increasing unbounded function. Threw a lot of words at you there. It just means it always gets bigger. So as b gets bigger, the natural log of b also gets bigger indefinitely. So the limit as b goes to infinity of the natural log of b is infinity. And to summarize, what that ends up giving us is that the area between the curve and the x-axis from x equals 1 to x equals infinity for 1 over x is infinite. And I mean, I think I should probably take a second here to talk about how surprising that is, because we have the integral from 1 to infinity of 1 over x squared dx from a previous example. That was only 1 unit of area, versus what we just did right now, which was the integral from 1 to infinity of 1 over x dx. You accumulate an infinite amount of area. Two very, very similar looking functions, two very, very similar looking integrands, and two completely different results in terms of the improper integral. So as you can see, our intuition, like I said before, is not necessarily the best thing to rely on. Infinity kind of throws everything out the window. So taking the limit of the integrand is not enough. We actually need to work these problems out. That's the whole point of what I was kind of developing here. You can't just look at the integrand and say, oh yeah, that's going to be a finite amount of area. You can't just look at a graph of the integrand either and say, oh yeah, that's going to be a finite amount of area. We've actually got to crunch the numbers. Luckily, you guys are awesome at crunching the numbers. So let's try another one. Okay, so example number 5. I've got some kind of cool stuff going on here. First of all, let's look at this integral. We're going to compute the integral from negative infinity to infinity of 1 over x squared plus 1 dx. This is improper on both ends, from negative infinity to positive infinity. So this region, actually, if you look at the region, it's going to go off to negative infinity on the left-hand side and to positive infinity on the right-hand side. But you can see in this graph that we've got that there's some symmetry that we can take advantage of. If you'd like, you could split this region up at x equals 0. And then if we just find the area between the curve and the x-axis from x equals 0 up to x equals infinity, then if we double that amount of area, that will give us the area of the whole region. So you could kind of exploit symmetry in your solutions sometimes. So let's try it. We have the improper integral from negative infinity to infinity of 1 over x squared plus 1 dx. Split it up at that point of symmetry. By the way, you don't have to take advantage of symmetry. That's not something that's required. It's just, I mean, it cuts down our work by a factor of 2. So if you could do half the work, that's kind of nice. So anyway, we split this up into the improper integral from negative infinity to 0 plus the improper integral from 0 to infinity. Now we made that observation about the symmetry of the region. So instead of doing 2 separate improper integrals, in this case we get lucky and we could do 1 improper integral, a single improper integral. We're going to go from 0 to infinity, and then we'll double that result. Okay, that was all our setup. But now, before we can go any further with antiderivatives and actually taking the integral and computing anything, we need to transition to a limit. That's the only way we have any computational abilities in this. So now we've got 2 times the limit as b goes to infinity of the integral from 0 to b of 1 over x squared plus 1 dx. And it turns out, you guys probably remember this from your top 20, the antiderivative of 1 over x squared plus 1 is the inverse tangent of x. Okay, and then beyond that, we need to plug x equals b and x equals 0 into the inverse tangent of x. I kind of skipped a step here in my notes, so I'll add it back in, but it's not strictly necessary. We have the inverse tangent of b minus the inverse tangent of 0. The reason I didn't write the inverse tangent of 0 is the inverse tangent of 0 is 0. So that's why I had left it out, but just in case you wanted to remember, that's going to be that inverse tangent of 0 equals 0. And I could show you why in a second. Okay, the short answer, the short solution that finishes this problem is that as b tends to infinity, the inverse tangent of b tends to pi over 2. So I'm going to give you the short answer to this problem first, and then we can go back and fix the rest of it at the end. So as b tends to infinity, the inverse tangent of b tends to pi over 2. And then as b tends to infinity, the inverse tangent of 0, doesn't matter what b is, the inverse tangent of 0 is independent of that, it equals 0. Okay, and then if you double pi over 2, if you do 2 times pi over 2, you've got your answer, pi. Here's the only thing I'm slightly concerned about. I'm not super concerned, but it's been a while since we've talked about inverse trig functions. You guys haven't really seen them much since last year, and so I want to make sure you guys are happy with the idea that the limit as b goes to infinity of the inverse tangent of b is equal to pi over 2. So let's go back to the graph paper I have on here, and just really briefly, I'll try to make this as fast as I can. Let's justify to ourselves that the limit as b goes to infinity of the inverse tangent of b is equal to pi over 2. Or for that matter, we could maybe justify to ourselves that the inverse tangent of 0 is equal to 0. I mean, that's probably just as worthwhile. Okay, let me grab an eraser quickly. Just kind of erase. Oh, does that work? Okay, well, it doesn't want me to erase. That's okay. All right, in any case, I probably don't need to erase. I can just draw over this. First, consider the regular old tangent function. Not inverse tangent, just regular old tangent. So y equals the tangent of x. And I almost wrote inverse tangent, but just tangent of x. Okay, y equals the tangent of x. It's got a vertical asymptote. We're just taking one branch of this, so just the branch that goes through the origin. But we've got vertical asymptotes. One at x equals negative pi over 2, and another one at x equals positive pi over 2. Okay, well, when we switch from a function to its inverse, a couple things happen. First of all, remember that the domain and range switch. So the domain of the original function is the range of the inverse, and the range of the original function is the domain of the inverse. So if I have vertical asymptotes at x equals negative pi over 2 and x equals positive pi over 2 for the regular old tangent, when I switch on over to the inverse tangent, you're going to end up having those as horizontal asymptotes. So the inverse tangent has horizontal asymptotes at y equals pi over 2 on top and y equals negative pi over 2 on the bottom. Now this graph is going to be reflected about the line y equals x. That's how you switch from the function to its inverse. And so the inverse tangent, I know it's kind of hard to follow this purple curve here, but the inverse tangent is going to look somewhat like the purple curve that I just graphed. So you could see that the inverse tangent of 0 is 0. That's the first thing you can kind of notice in here. That inverse tangent of 0 is equal to 0. So that's certainly true. And now if you try to follow this purple curve as x goes to infinity, and now it's going to be a red curve, you could see that the inverse tangent is approaching this horizontal asymptote of y equals pi over 2. And so you could kind of verify for yourself in this fashion that the limit as b goes to infinity of the inverse tangent of b is equal to pi over 2. Okay, I know that's kind of a mess because there's a ton going on here, but that's example 5. By the way, remember that if at any point you need anything paused or rewound, I guess rewound would be the word, just make sure to ask your teacher, and they'll be happy to do it. Okay, let's move on to example number 6. This will be our last example, and then I just have a couple slides with some notes that I'd like you to have in your notebook so you can refer back to. Okay, there we go. Now we're on to example number 6. So for example number 6, the only reason that I've included this slide is because this integral is kind of a doozy to compute. The reason being, the only way to take this antiderivative will be to use integration by parts. But before we get to integration by parts, before we get to antiderivatives, we always want to reframe the problem in terms of a limit. So let's rewrite this as the limit as b goes to infinity of the definite integral from 0 to b of x times e to the negative x dx. All right, now that we've got a limit, now we can worry about integration by parts and all that sort of good stuff. So let me just remind you of the integration by parts formula. It's the integral of u dv is going to equal uv minus the integral of v du. And that will actually work pretty darn well for this particular scenario. What I'm going to do is I'm going to let x equal u, and I'm going to let e to the negative x equal my dv. Okay, so that means that my du is equal to dx, and that also means that negative e to the negative x is my v. And then there's supposed to be a little dx there. Okay, looks like we're ready to go. So what I'm going to do is I'm going to plug into the formula uv minus the integral of v du in the next step. So x is my u. I wonder if there's a highlighter on this. Let me see quickly. Yeah, I could set transparency actually. Let's try this. I don't know how well it's going to work, but so if u is equal to x, replace u with x. And then if my v is equal to negative e to the negative x, then v is negative e to the negative x. And then minus the integral of v du. Okay, well my v is, once again, negative e to the negative x right here. So plug that in, negative e to the negative x. And my du is dx. There it is. Okay, so just straightforward integration by parts there. The only thing that kind of throws a wrench in the works, the thing that you have to be kind of careful with is, let me switch this back to a pen now. Sorry about that. Okay, the thing you have to be careful with is basically just the fundamental theorem of calculus. We have to make sure that we get these limits of integration worked in somehow. So we have this negative x e to the negative x. That needs to be evaluated at 0 and at b. And this integral of negative e to the negative x dx, we need limits of integration there as well, from 0 to b. All right, now we are in a position where we have an integrand that it's easy to find the antiderivative of. The antiderivative of negative e to the negative x is e to the negative x. And then we are going to plug in x equals b for both of these. We're going to plug in x equals 0 for both of these. So we've got negative b e to the negative b minus 0 minus the quantity e to the negative b minus e to the 0. You just apply the fundamental theorem of calculus here, and you plug in x equals b and x equals 0. All right, well, it would be perfectly valid for you to interpret negative b e to the negative b as negative b over e to the b. Likewise, it would be perfectly valid to interpret e to the negative b as 1 over e to the b. The reason that's useful is if we're taking the limit as b goes to infinity, well, the limit as b goes to infinity of negative b over e to the b, this is going to go to 0. And then this 0 right here is also 0. It's already 0. And then 1 over e to the b, as b goes to infinity, that's going to go to 0. So e to the negative b goes to 0. And the only thing we're actually left with is, let me grab a different color here so it kind of shows up. We have negative e to the 0. We have the opposite of negative e to the 0. Well, minus a negative is plus a positive, and e to the 0 is equal to 1. And there we have it. Our answer is 1. Let me zoom out so you can see everything all at once. And then if anybody does want this paused, feel free to ask the teacher, and they can do so. And then we can move on from there. All right, so that's all the examples. Let me, I just have a couple slides of notes. Nothing wild here, just some summary and some stuff that you're going to want recorded in your notes. So first things first, let's go to just a formalization of this, of the improper integral. Okay, so what you can see here is if f of x is a continuous function, then the way that we're supposed to interpret the improper integral from a to infinity of f of x dx is as a limit. The limit as b goes to infinity of the definite integral from a to b of f of x dx, which is kind of a definition. I do want that definition in your notes, though. I want this to be something you can refer back to later. We could also take the improper integral from negative infinity up to a finite b, and that just means to take the limit as a goes to negative infinity as of the definite integral from a to b of f of x dx. Okay, so these are just kind of definitions here of improper integrals. And then the other thing that you're meant to keep in mind is you can actually have an improper integral where it's improper at both ends of the integration, at both limits of integration. So we can go from negative infinity up to positive infinity, and the best way to do this is to break it apart into two different integrals, improper integrals. So from negative infinity up to some finite value c, and from c up to infinity. And you get to pick what c value you use. My advice would be to try to pick a c value that gives you symmetry for the two regions, so that you only have to do one integral and double your answer. Of course, that's only going to work for even functions or other functions that might have symmetry about a vertical line somewhere where you can kind of pick a clever spot for setting your c. So that won't always work, but when it does, it saves you a lot of time. All right, and then moving on from that, this is just some summary. There were some important ideas in this lesson, and I want to make sure you go home with those ideas. So let's take a look at it. So first of all, I want you to remember that not all improper integrals converge. And sometimes it's obvious if they're going to diverge, right? Like we had an example where our function was f of x equals, we had f of x equals 4, I guess. It was a constant function. And so the amount of area that we accumulated was infinite. So sometimes it's obvious when you have an improper integral that's going to diverge. Sometimes it's not so obvious, though. I mean, look at these other two examples we had. We had the integral from 1 to infinity of 1 over x squared dx, which only accumulated 1 unit of area, versus the improper integral from 1 to infinity of 1 over x dx, which accumulates an infinite amount of area between the curve and the x-axis. I mentioned this before, but our intuition for how numbers should behave and how functions should behave falls apart a little bit once we start talking about the infinite. Once we're working with infinity, some of our intuition breaks down. So you got to do the work. You actually have to crunch the numbers. You can't just look at a graph or the integrands to see if the integral converges. Now you might be able to look at the graph or the integrand to see if the integral diverges. Recognizing divergence sometimes can be obvious, like this constant function we had, but recognizing definite convergence can be tough. With this last, let me leave you with this last slide here. It's kind of a little bit of a theorem. I don't know if that's the right name for it or not. But consider the improper integral from a to infinity of f of x dx. One thing we did notice is that if we want our improper integral to converge, the only way that it even has a chance of converging is if the integrand, when graphed, tapers off as x goes to infinity, right? Kind of has to taper off as x gets large. So if it doesn't taper off, essentially if the limit as x goes to infinity of f of x does not equal 0, then for sure your improper integral diverges. So if the function, if the integrand does not taper off to the right, if the limit of that function doesn't go to 0, then the improper integral, with beyond a shadow of a doubt, like most definitely diverges. On the other hand, if the integrand does taper off, if the limit as x goes to infinity of f of x does equal 0, it may or may not converge. We don't know. It could be like that 1 over x squared integrand, where the integral from 1 to infinity of 1 over x squared dx went to 1, or it could be like that the integral from 1 to infinity of 1 over x without the squared dx, which went to infinity. By the way, you'll see this phrase in future math classes, but in the world of math, this is called a necessary but not sufficient condition for convergence. It is necessary for the limit as x goes to infinity of f of x to equal 0 in order for the integral to have a chance of converging. But it's that being true, this condition being met is not sufficient for showing that the integral converges. So it's a necessary step, but it's not enough. You got to do more work than that. And that's the lesson for today. So I hope you guys enjoyed it. I think out of all 3 takes, my second one was the best because the first time I had a lot of enthusiasm, but then I had to like fix a couple things I miswrote. The second time I still had my enthusiasm, but then I fixed up any little writing errors that I had messed up the first time. This third time, I think the math went very smoothly, but I am tired, guys. I'm going to go take a nap. Have a great day. Bye-bye.